Now that we have learned how to design and generate levels or terrains in video games, let us have a more detailed look into how to create realistically looking things that move. 3D modeling refers to the process of creating three-dimensional representations of objects or characters using specialized software. These models can then be animated and rendered to appear realistic or stylized, depending on the artistic direction of the game. There are at least three types of 3D models in games. The characters, such as the player and non-playable characters, require special attention to look and move in a realistic manner. Environments include either natural landscapes or cities, houses, and interiors of rooms. Props and assets are in-game items such as weapons, vehicles, and furniture, which can be static or movable. Before modeling begins, artists and designers usually draft concept art. Using software like Blender, artists create 3D models. They start with basic shape, such as a cube or a sphere, and refine it by adding details. Once the model is finalized, it's time to add colors, patterns, and details. This is done by creating and applying 2D images known as textures onto the model. If the model needs to move or be animated, like a character, a virtual skeleton is created, which is called rigging. A polygon mesh is a foundational concept in 3D graphics and is central to representing three-dimensional objects in digital space. It is a collection of vertices, edges, and faces that defines the shape of a 3D object in computer graphics. Each face usually consists of a flat polygon, and the most common types of polygon used are triangles or quadrilaterals because they are computationally simpler to handle. With proper rigging, these meshes can be deformed and moved around to simulate lifelike movements. A very important consideration in 3D modeling is the polygon count. The more polygons, the better the result, namely the more naturally looking 3D model. However, the more polygons, the more computer memory and the more processing power is required. A dense mesh has many polygons packed closely together. While this can capture intricate details, it can also be computationally intensive. Conversely, a sparse or low-poly mesh may not capture fine details, but it will be faster to render. In video games, where real-time rendering is a must for a smooth experience, too many polygons can slow down the frame rate and affect gameplay. Here, developers need to consider the capabilities of their target platform. A high-end gaming PC can handle far more polygons than a mobile device. On the other hand, games designed for mobiles or VR typically have a stricter polygon budget due to performance constraints. A nice trick is used with the size of the characters. As a character or object moves farther from the player's view, a less detailed version of the model might be used to save on processing power. This system of using multiple detail levels for one object is called level of detail or LOD. The process of projecting a 3D model surface onto a 2D plane to create a coordinate system is called UV mapping. If you imagine a 3D mesh as a hollow plastic toy, UV mapping would be similar to cutting up and flattening this toy so that you can paint over it. This flattened out version lets you determine how a 2D texture aligns with the 3D geometry of the model. The process of making a 3D model move is typically described in the context of rigging and animation. In rigging, a virtual skeleton is created and placed inside the model. This skeleton is made up of bones, which are hierarchical structures that define how different parts of the model move in relation to one another. The next step is to bind the 3D model's mesh, its outer layer, to the skeleton. This process, called skinning, ensures that when a bone is moved, the correct part of the model's mesh moves with it. Not all parts of the mesh should move equally with the bones. For instance, a bone in a character's upper arm should have a lot of influence over the muscles of the upper arm, but less influence on the lower arm or chest. Once rigging is complete, the animation process begins. The most common technique is keyframing, where the animator sets specific poses for the model at certain points in time, known as keyframes. The software then interpolates the movement between these keyframes, creating smooth transitions between poses. To move hierarchical chain-like structures, such as arms and legs, forward and inverse kinematics are used. In forward kinematics, the movement of parent bone directly influences the position of child bones. If you move the upper arm, parent, the forearm and hand, which are children, will follow. On the other hand, inverse kinematics allows for the end of a bone chain to dictate the position of the preceding bones. For instance, by moving a character's hand, end of chain, the elbow and shoulder will adjust automatically to accommodate that position. To circumvent the animation process that can be rather complex, motion capture is sometimes used to produce very realistic results. For certain types of movements like flowing hair, cloth or fluids, it's more efficient to use physics simulation than to animate manually. The software calculates how these objects should move based on factors like gravity, wind and collisions. At the end of the unit, you will find several questions to test your knowledge. Here is one of the questions. What is UV mapping used for? Is it to see how a model would look under UV light? Or is it to map a 3D mesh to a 2D space to apply textures? Or is it to calculate the distances between the edges of polygons on different sides of a 3D mesh? Or is it to reduce the processing power when the character is far from the camera? What do you think?